So in this video we can go over on how we can be able to have another form of actually energy, which is a kinetic energy and also the wake energy theorem. A piece of remind, we know that, let's say if this is the object and I say the object has been subjected to the forces given as, let's say, F, and assuming that the force has displaced the object and that was some distance given as, let's say, S. Now since there is a distance be covered upon having the force F on the object, then we say actually the wake has been done on the object, given as wake is equal to the force times distance, and basically the wake is given actually in joules. So now we'd like to discuss another form of energy associated with the motion of the object, which is a kinetic energy, and further we'll look at what you call the wake energy theorem. So now let's say we have the object and which is given as this, and I say the object is of mass, let's say the object is of mass given as m, and say this is, let's say, a point A, and say the object, the force given as F has been applied on the object, and say at the point A the object is having the initial velocity, let's say, given as u. Now since the force has been applied, let's say the force is constant force. Now since the force has been applied, the object will have to displace and at some distance, let's say to point B, and the distance let's say it is given as, let's say, S. That's the distance or the displacement that the object is possessing. Now let's say at the point B the object is having the new velocity given as, let's say, v. Now since the force being applied as a constant force, then the object from the fact that the object from the fact that the velocity has changed from initial to final, where then we say the object has accelerated, and the acceleration will be the constant acceleration because the force being applied is the constant force. So now the acceleration will be towards the same direction, which is given as this acceleration. So now according to the Newton's second law of motion, we have the force responsible for the motion, which is equal to the mass times acceleration. And this is according to the Newton's second law of motion. And on the same case, acceleration can also be given as force of mass, and of which the mass has to be in kgs, the force has to be newtons. So at the end of the day, acceleration is given in meters per second. So now we can be able to have the relationship exist among the initial velocity, final velocity, acceleration, as well as the displacement, using one of the equations of kinematics. And what is that? So in this case, we'll have it as v square is equal to u square and plus 2as. So this is the formula you should have to understand, and that actually expresses the relationship exists among these actually four parameters. So now let's think of having this as the subject formula. So in this case we'll have it as 2as, and which is equal to, now v square now should be v square and minus u square. We'll have that understand. Then let's think of dividing both sides by 2. And of course, let's first of all substitute what is the acceleration. This acceleration, it is the same as this acceleration, and hence we'll have it as this. So which means we'll have 2 times force of mass and times the displacement, and which is equal to v square, that is v square minus u square, which is that. And the further arrangements will have it as 2 fs and divided by the mass, and which is equal to v square, which is equal to v square minus u square. So now for this case, let's think of actually multiplying both sides by m. So which means we'll have it as 2fs. Now we'll have 2fs, that which is equal to mv square and then minus mu square. So now we'll have it as, and of which now we can have it as this. And of which we'll have it as 2fs, and which is equal to mv square, that is mv square. So what's happening here? mv square minus mu square. So now let's think of dividing both sides by 2 and see what I can do have. So in this case, we'll have it as fs, and which is equal to, now should be mv square, and divide by 2, and minus mu square, and divide by 2. And of which this is the same as having it as fs, and which is equal to half, and that is half mv square, that is half mv square minus, should be half mu square. So now in this case, what I'm going to have is, and that is now now we have fs, which is the first times distance, now being given as half mv square and minus half mu square, of which fs corresponds to the work done. And what is this work done? So now this work done corresponds to the motion of the object. Now this work done is what we call the kinetic energy. So this is the energy due to the motion of the object, which is given as half mv square. So whichever the case, whenever the object is moving, let's say can be at a constant speed. So as the object is moving at a constant speed, and this is the actually energy it is possessing, which is given as the kinetic energy. So unlike whenever the object is moving at a constant speed, where the work done is literally being said to be zero, but whenever the object is moving at constant speed, the energy associated to that object is given as the kinetic energy, which is given as half mv square. So you should have to understand that and up to. So now, since this actual work done, which is fs, it is more associated with the entire journey of the object from initial velocity to the final velocity, then this is what we call the actually total work done. So this is said to be the total work done, and since it is for the whole entire journey for the object, and from initial velocity to final velocity, so that is said to be the total work done. And also, since the energy associated with the motion of the object, which is half mv square, it is given as the kinetic energy, and from the fact that the object is changing the velocity from initial to final, then this is should be initial kinetic energy, and this is the final kinetic energy, you can see. So now, since we have the final kinetic energy minus the initial kinetic energy, then what we are having here corresponds to the change in kinetic energy, which is given as delta Ka. So this is what we call the work energy theorem, which is said to be the total work done on the object is the same as the change in the kinetic energy of that particular object. So this is what we call the work energy theorem. So please keep that in mind. So this is what it means. So now which means the total work done on the object, and therefore the motion of the object, is equal to the final kinetic energy, and that should be minus the initial kinetic energy. So this is what you call the work energy theorem. You can know. So now, which means, as you can see, the faster the object is moving, the more kinetic energy in that particular object is possessing. So that's what you call the work done, and also should be that's what you call the kinetic energy and the work energy theorem. Really, this is the energy associated with the motion of the object, and that is the energy with respect to the speed of the object. So now let's say this is the question. A small airplane moving along the runway during the takeoff has a mass of, it should be 690 kgs. So that is the mass. 690 kgs should be the, by the way, the mass has to be given in kgs, and has a kinetic energy of, what is the kinetic energy? 25,000, and that should be joules. So the question says, what is the speed and of the plane? So we are looking for the speed. So in this case, we're going to use the formula for the kinetic energy. So in this case, we'll have the kinetic energy is equal to half mv squared. So substitute the kinetic energy and the mass you saw for the actually speed of the object. So try to have that out on your own. Let's say this is the question. A 220 kg motorcycle. Now we have the mass, that is 220 kgs. Should be 220 kg motorcycle is cruising at, that's the initial velocity. 14 meters. That should be 14 meters per second. Now, what is the total work done? So now we are looking for the total work done. So it should be the total work done. We are looking for the total work done. So total work done, that's what we are looking for. And on the motorcycle, to increase its speed to 90 meters per second. Now what we have, it is the final velocity, 90 meters per second. So now how should we have the total work done? We're going to use the work energy theorem, which states that the total work done, it is given as the change in the kinetic energy, which is the final kinetic energy, and minus the initial kinetic energy. So actually the final velocity will help us to have the final kinetic energy, and the initial velocity will help us to have the initial kinetic energy. That will be given as the total work done. So try to have that at your own time. So now let's say this is the case, and I should have it at, when a father takes his daughter out for a spin in a stroller, he exerts a force F with a magnitude of, should be 44.0 newtons at an angle of 32 degrees below the horizon. The stroller and the child together have a mass of 22.7 kgs. So now in this case, we should have to come up with a free-body diagram showing the system. You know, let's say this is a child. Let's depict, let's say this is a stroller and a child, and both with the mass given as 22. And that should be with the mass given as I must have in that way. And let's say the father is applying the force, and which is going over in that way, and the force is said to be at an angle of, should be at an angle of 32 degrees, and should be below the horizon. I should have it this way. Let's say this is the case. Now it is said that the force is at an angle, this, and that should be 32. What is happening here? We have 32. Anyway, we should have it as 32 degrees. Let's say that's the case, and where this is the force. And the object happens to move and having the distance of, and that should be 1 point. Should be 1 point. What is going on here with my pen? Should be 1 point 1 should be 1.13 actual meters. Now should be that's the displacement given as t. So now the question says, how much weight does the father do on the straw when he pushes it through a horizontal distance of that one? So now in this case, the weight done will be given as the force times the distance. Now since the force has been applied at an angle, then we'll have the component of the force which is in line with the direction of the motion. And you have to resolve the force F into components. You see that the F component, you see that the X component will be the one responsible for the motion. And that since the motion is along x-axis, so which means the X component of the force will be responsible for the motion. So that will give us the actual weight done. And by the way, that particular weight done will also be said to be the total weight done, because it is the amount of energy responsible for the motion for the whole entire journey of the object. So that will be given as that. And of which we'll have it as F cos theta. F cos theta times the distance. That will be given as the weight done. And also that will be regarded as the total weight done and for the object. Now the question B says, if the initial speed of the stroller is, now we have the initial speed. I will be looking for the final speed. So I'm going to use the total, we're going to use the work energy theorem, and I'll be able to have the final speed. So the total weight done is equal, the final kinetic energy. And that should be minus the initial kinetic energy. So I'll be able to have, the final velocity on the final kinetic energy as the subject formula also for that one. So keep that in mind. So now let's say we have this problem. How much weight is needed? How much weight is needed for a 73 kg runner to accelerate from rest to 7.7 meters per second? So we have been given the mass 73 kgs, and we have the initial velocity which is given as L, and we have the final velocity given as 7.7 meters per second. It should be 7.7 meters per second. So now we are looking for the total weight done. So now we're going to use the work energy theorem to have the total weight done in that case. So try to have it out at your own time. Now let's say this is the problem. A 9.5 gram plate has a speed of 1.3 kilometer per second. So we are being given the mass, which is given as 9.50 grams, and of course has to be in actual kgs. So simply we just have to divide this by 1000 to have the mass in kgs, and of course we should have it in kgs. and the speed of should be, we have the speed which is given as 1.30 kilometer per seconds. And the thing is that we are not being told about anything to do with the change in the speed. Literally, this is the speed in which the object is moving with. It can be at a constant speed. Now, the speed has been given in kilometers per second, and of which has to be in meters per second. Then we'll convert 1.3 kilometers and to have it in actually in meters. So which means we need to convert 1.3 kilometer to be in meters by just multiplying this by 1000, and we'll have the velocity in meters per second. Then what is its kinetic energy in joules? Then we use the formula for the kinetic energy to have the solution there. And the question B says, what is the body's kinetic energy if its speed is halved? So which means if this one has been divided by 2, what will be the actually kinetic energy? So which means we just have to simply divide this by 2, then we'll have to solve for the kinetic energy. Likewise, the question C says if its speed is doubled, so which means we'll have to multiply this one by 2, then we'll have the kinetic energy. So try to have that at your own time. So now let's also have to appreciate this kind of equation. The energy required to increase the speed of a certain car now should be from 18 meters per second, that's the initial velocity, should be 18 meters per second, and up to 24 meters per second, that's the final velocity, should be 24 meters per second. And the energy is given as 190 kilojoules. So that's the should be a kinetic energy. That is and there should be, this is the total work done. This is the total work done. So we have it as 190 kilojoules, of which has to be in actual joules, so which means we'll multiply this by 1000 to have it in joules. So what is the mass of the car? So which means we're going to use the work energy theorem to have the mass. And the question B says, at what speed is the car's kinetic energy equal to 190 kilojoules? What does it mean here? So the question B says, at what speed is the car's kinetic energy equal to, and that should be 190 kilojoules. So in this case, we just have to simply use the kinetic energy formula. That is kinetic energy that is equal to half mv square, of which we have the kinetic energy and we have got the mass of the object, that is the car, in the part question A. Then we'll be able to solve for the actually that particular speed. So keep that in mind. So again, you have that at your own. That is. So finally, if my videos are impressing you, please don't forget to subscribe my YouTube channel. That's a part of the supporting system. Thank you.